So last week we went through the all about shapes and we got as far as, we did the square, the rectangle, the parallelogram, and the rhombus is a special parallelogram. A rhombus has 4 sides, each side having the same length. This angle and this angle are going to be the same, and this angle and this angle are going to be the same. So to get the area of that, it's just going to be the same as getting the area of a parallelogram. Lines of symmetry and a little bit of information there. This shape here we also touched on with its name of trapezium, and we just considered it to be 2 triangles, one with a base of A, one with a base of B, and this height being the vertical height, so not the slanty height. And the area of that was a half A plus B times H. It's easy to see the proof of that formula because this triangle here is going to be a half AH, and this triangle here is going to be a half BH because the base is here and the height is there. Both triangles have the same height. There's A's height, there's A's base. Okay? So the trapezium, if we add this and this together, algebraically that is actually the same. So that's area of a trapezium. If you were trying to get the perimeter of a trapezium, you would simply add up this length plus this length plus this length plus this length, and they're going to be 4 different lengths, which you would be given. How many lines of symmetry? It doesn't, but an isosceles trapezium does, because you actually have these angles here the same, and a mirror line going through that way that would fold onto itself. Okay, properties of a trapezium. What's this one? A kite. So it's, yeah, and so it's actually not a parallelogram. So to get the area of this, again, you could treat it as these 2 triangles. So it's quite a good technique for any shape to split it into other shapes to work out this area. Alrighty, now moving on to today's lessons of triangles. This is what I expect you to already know. An equilateral triangle actually has 3 sides where each side is the same length. So it might be indicated by something like that to say those 3 sides are the same length. When the 3 sides are the same length, the angle is actually 60 degrees. Always. Okay? Angles in a triangle always add up to 180. So because of that, you can see if I folded it through this line, it would fold onto itself, this line it would fold onto itself, and that line it would fold onto itself. So it's actually got 3 lines of symmetry. It's a special triangle, an equilateral triangle. How would I get the area of that triangle? I would go the base times height. Notice the height is the distance between here and here, if that was parallel to there. The height is not the slanty bit. Okay? Next one. Oh, yep, I've probably said that. And that's geometry. It's not actually measurement there, so we won't worry about that at the minute. This one here is called an isosceles triangle. And what happens with an isosceles triangle is this length here and that length there are the same. So this angle here and that angle there are the same. Okay? If we were to get the area of this, again, we'd use this base and the height here. Okay? we don't use the slanty height. If we were trying to find the perimeter, we would just add up this length plus this length plus that length. Okay. Now what's this one called? A scalene. A scalene is where the three lengths and the three angles are different. How would I find the area of this? That I would call my base, and that I would call my height. Okay? If the triangle was, doesn't matter which way around it is, you can choose any base, and then you've got to, well, that one, if it was a right angle, I could use that as my height. There's nothing stopping me saying that that's my base, and then I'd have to find out, well, what's my vertical height would be here at right angles. But it kind of makes it more tricky. It's easier to use the base of whatever's actually on the bottom. Okay. I just want to show you, if the triangle was like that, that's still a scalene triangle. And the height of that, if we called this here the base, between here and here, the height would actually be here. Okay? So that's one thing to watch with the triangles and things, is the perimeter, quite easy, that you add up this length plus that length, but the height sometimes is a little bit hard to see because it can actually exist outside of the triangle. Okay. What type of triangle is that? Right angle. Equilateral is where they're all three sides are the same, so they're all 60 degrees, whereas that one there is actually 90 degrees. Quite often you get this sort of one for area because it's quite handy that that height is actually also a side of the triangle. So that's where I think people get the idea that they can use the side of the triangle, is that because they've dealt with 90 degree angles. So here the area equals base times height. Okay, there we go. It can be scalene, it can be isosceles, so you can actually have it where these two are the same length. Okay, or three different lengths. Okay, you're going to get a line of symmetry if it's isosceles, otherwise you won't. There we go. So we have some language. Does anyone know what vertex is? Perpendicular, parallel, diagonal. That's all geometries. It's not actually measurement, but we're measuring these shapes. So it's still quite nice to have a look at the language. Parallel lines never meet. They're always the same distance apart. Perpendicular, they meet at right angles. So it's smack bang in the middle. That one there is like 180 degrees, and these are 90 degrees. Whoops, 90 degrees and 90 degrees. Okay. Next one, vertex, that's the corner, okay? So it's a language thing that these are the vertexes. Diagonal is when you go from one vertex to the opposite vertex. It's a diagonal distance. Bisect, bi means two, okay? So when you bisect, you cut it exactly in half. So this is right in the middle. That length there and that length there would be the same. A regular shape, all of the angles and all of the sides are the same. So that's like our equilateral triangle or our square. Parallel, perpendicular, vertex, diagonal, bisect. Should know what they are. Polygons, shapes with many sides. So a polygon is a two-dimensional figure with straight sides. So you start off with a triangle, and we had types of triangles. Then you have a quadrilateral, and we had multiple types of quadrilaterals, and then this has the 1, 2, 3, 4, 5 sides, and it's a pentagon. Oh, sorry, that jumped ahead, didn't it? Whoops, we didn't get to a pentagon. Where did we go? We actually went straight to a hexagon for 6, and 6 lines of symmetry, because that's a regular hexagon. So all of those lines and all of those angles are the same. That's my favourite, the pentagon. So we have got 5 lines of symmetry, 5 angles the same, 5 sides the same length. So that's a regular pentagon. With regular pentagons, you can make a beautiful shape called a dodecahedron, which is actually my favourite shape. I'll show you a dice of the dodecahedron later. Eh? No. Oh, what are we talking about? Oh no, dodecahedron, hang on, I'll show you. So tetrahedron, the platonic solid, is a regular convex polyhedron. So the faces are regular polygons, okay? So here I've got 4, if I push animation I think it'll maybe help. So here I've got 4, whoops, sorry. There are 4 equilateral triangles to make up this tetrahedron. Not my favourite shape. Nice, but not as good. So here's the dodecahedron. There's 12 faces, but each face is a regular pentagon. And these platonic solids, there's only 5 that exist. So that's a dodecahedron here. So you've got to start with a regular polygon and then put them together so that you've got this platonic solid. And there's only 5 possible combinations. So with an equilateral triangle, you can get, so an equilateral triangle, you can get your tetrahedron, your octahedron, so 8 equilateral triangles, or your icosahedron, which is actually also very nice, with 20 equilateral triangles. With your square, you can make a cube, nothing else. Right, that is a platonic solid. And then the dodecahedron, pentagon, 12 of them. Beautiful shape, really cool. Okay. Almost there, so we've got that pentagon and polygons, shapes with many sides, looking at lines of symmetry. Can you suggest a rule? So there we've got a triangle, 3 sides, 3 lines of symmetry. Yep.
The amount of sides it has is the amount of lines of symmetry?
Yeah, when it's a regular polygon. Yeah, exactly. All sides the same length, all the angles are equal, have the same number of lines of symmetry as the number of sides. That's some cool algebra there. So a heptagon and an octagon, 7 and 8. A nonagon is a one with 9 sides, isn't it? Yeah. And I'm going to show you now, I think you deserve the polygon song. Na 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 na, just a boring square. I wish I was a pentagon, but I am just a square.
Na 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 na, just a boring square. I wish I was a pentagon, but I am just a square. I wish I was a pentagon, but I am just a square. My sides equal 4, but if I had one more, I'd be a pentagon and not a square. Na 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 na, just a boring square. I wish I was a hexagon, but I am just a square. If I was a hexagon, then I wouldn't care. My sides would equal 6 if they were made of sticks. I'd be a hexagon and not a square. I've always been a square, and